speaker is Olof Karlsson, and he's going to talk about studying Scala with records. Thank you.
All right, thanks. My name, as you said, Olof Karlsson, and I spend my time working as a consultant for a small consulting firm called Consulting, but also work as a developer for a fintech startup called Grims Nordic. And I would like to start with thanking both of these companies for actually supporting this work, since I've done part of it on paid office hours. And I've written this paper together with Philip Haller from KTH, Royal Institute of Technology, sitting right there, some of you might know him. Right, so today I would like to talk to you about how you can actually, with some new features of Scala 3, if you combine those with some fairly small additions or changes to the compiler, you can actually achieve structurally typed extensible records for Scala. And I would also like to talk to you about how we have implemented this in a fork of Dari, and show you some performance benchmarks we have made to evaluate the runtime performance of these records compared to alternative implementations, but also nominally typed case classes, for example. So what do I mean by records, since all different languages define records in different ways? Well, semi-formal definition here. A record is a collection of label value pairs that we call fields. So here, for example, I create this conf record with two fields, name and year. And of course, you should be able to access these fields by label. In this case, using the dot notation here to get the corresponding value. But most importantly, we want this record to be structurally typed automatically. So once you create a record like this, it would get this structural type here, in this case, as a structural refinement. But we also want these records to be extensible, so you can have an existing record like conf there, and then you can add a field, like the city field with the value St. Louis, and this field should be reflected in the return type. So the result of this would be a record with 3 fields in this case. And there exist some libraries to achieve this in Scala 2, but unfortunately all of them seem to have some weaknesses. They're not entirely satisfactory. For example, there's a library called Scala Records, and these records, they are not extensible. So what you can do basically is you can create these records and then access the fields, but that's it. Then we have the Compostable Library. It is extensible, kind of, but it's not type safe. So if you add a field that already exists on a record, but with a conflicting type, you will get a runtime error. So that's not good. Then, of course, we have the famous Shapeless library with their H-list-based records, and they are for sure extensible among a lot of other things you can do with them. But the Shapeless records, the fields of those records are ordered, so like a name and a year record isn't the same thing as a year and a name record, and that is really limiting. It essentially breaks structural subtyping. Furthermore, all of these libraries for Scala 2, they rely on white box macros, which are deprecated, and they will definitely be gone for Scala 3. So like the whole foundation for these libraries will just like disappear. So we need something better. So we created this list of design goals for what we would like these records to have. We want a record constructor, obviously, that would create like a record primitive. We want them to be structurally typed and have unordered fields in contrast to shapeless. We want extensibility and should be type safe in contrast to compostable. And we want no dependency on the deprecated macro system. Furthermore, we want to do this with as small changes as possible to Scala's type system, right? And we don't want to add any new like special syntax to the language. So we want to achieve as much as possible with as small changes as possible. And to do this, we begin by using a new cool feature of Scala 3, which is this selectable trait that takes you quite far, actually. So to see how this works, I would like to compare with structural field access in Scala 2. Let's say that you have an instance here with a structural refinement type. What happens if you access this field here, as explained in the keynote before? What would happen is a reflective call. So on the JVM, you would get the class, you would search for the method here, you would invoke it, and the compiler would cast the result. So the compiler would like translate this call to roughly this reflective call with some caching on top to like optimize performance. But in Scala 3, you can implement, if you implement this interface here, something special happens. So since this instance inherits from selectable, what would actually happen is that the compiler would translate this call to a call to select dynamic, give the implementer the label of the accessed field, and do a cast. And since it's structured with type, you would of course also get the type safety. So if you access some field that clearly isn't on the record, you will get a compile time error. And this brings you, this makes it extremely easy to build like a basic record implementation just using Scala 3 features as a library. So you could create this case class here, record, and it has like a map as an underlying data structure from label to value. It extends selectable, so you get this new structural field access. And then you provide the obvious implementation of the select dynamic method. So when the compiler passes you the access label, we just look it up in the map and give the value back. So you would use this record in this way. You can create a record R here. You just instantiate the record class, provide the values of the map. But then you would have to cast this record yourself to a structural refinement type by just have this as instance of. So you would have to like give this type explicitly yourself. But once you have that, you would get this new Scala 3 structural field access. So if you access the year field here on this record, it will translate it to select dynamic, pass you the year, the implementation would look it up in the map, and then cast it. So this is great, but compared to our design goals, it has like two major flaws. So the first one is this cast here. First of all, it's very verbose. I mean, you would have to write this yourself, so it isn't automatically typed as a structural refinement type. And secondly, it's really like a single point of failure here, since if you get this type wrong, you lose all the type safety. And it's very easily to get this wrong. I mean, yeah. And secondly, this doesn't give us any way of like extending these records. So we have basically two problems: a type-safe constructor and a type-safe extensibility. And in this paper, we show how we can solve both of these problems with a single solution. And that is to, if we solve extensibility, we will get a constructor for free. Because it's really easy to, like this we can do in a type-safe way, create an empty record, and then to construct them, we just add one field at a time. So this would be our way of like constructing a structurally typed record in a safe way. So to solve extensibility, we use a second new feature of Scala 3, which is the cool intersection types, which allow you to write something like this. I'm sorry for the boring example, but so yeah, you can basically declare it that a type C should be both an A and an E. And this is really attractive for extending records, since they work out really great with structural refinement types. So you can take an intersection between two record types, this with a name field and one with a year field, and this would actually be equivalent to just the record with both of these fields, which makes it extremely tempting to implement a concat method like this. It takes one record S of type capital S and another one type capital T. Just merge the underlying maps here to get the fields of both of them, and then type the result as the intersection of both of these records. Unfortunately, this doesn't really work out that great, because this is the same implementation as before. What happens if you try to concatenate these two records? They have a conflicting label here with different types. One has this Roman literal, and one is an integer. So what would happen when you concatenate them is that this map concatenation has the semantics of overwriting from the right. So what you would end up with is a record with an integer 2008 field. But that is not how like intersection of refinement types is defined. That is defined recursively. So the resulting type would be year of type string and int, and that is of course wrong. So when you select this field, you will get a really ugly runtime exception. And this, I was so happy when I discovered this. This is actually what happens if you try to concatenate two records in TypeScript. So at least they can listen to this and find it interesting. Yeah. But so like a naive solution to this would be to demand that S and T here are disjoint. So what happens if we introduce like this type class disjoint here that acts as a proof that S and T are disjoint? Then it should be safe, right? Because we don't get this conflict of like different types in the same field. Well, look at this example. You have the same records from before, like one with Roman year and one with an integer year. But due to structural subtyping, this is an equally valid typing of this record. And of course, these two types, they are disjoint statically, so it would be possible to call concat here. Unfortunately, we still have this value here that would override, so now we end up with something maybe even worse, because now we have a record with like an integer field here, but the type is string. So again, you get ugly runtime exceptions. So the way we have solved this is, okay, forget about concatenation, let's do extension instead. Let's extend the record with a single field at a time. And it has to be a statically known field, and furthermore, we demand that the resulting record, you have to be able to type that correctly using intersection types. And that is basically captured by our little half-formal soundness rule here that essentially says that we're allowed to extend a record with a field if it doesn't exist before at all, or if it exists, the new value must have a subtype of the existing type, because then it would work out with using intersection type to like type the result. To implement this, we do our first, this is like our first contribution or extension to the Dotty compiler. So we introduce this extensible type class here that essentially says that the soundness rule is fulfilled. So an instance of this guy would say that this record R here is extensible with a field with label L and type B. So we replace the concat method with an extend method, allowing you to extend R with label L, value V, only if you can provide an instance of this proof here, using implicits. So the way this would work is that assume you have this value R as this type, you extend it with a year field, and here of course the compiler will start searching for this implicit proof, right? And then our addition is that we synthesize it automatically. So if you don't have it in scope already. So since in this case it's safe to extend, the compiler will automatically insert this guy for you. A small little problem hidden in this slide though. Now we don't have a proper intersection type. Before we had two record types that we could intersect. Now we have a record type and a label value pair, so we don't know what to write in this intersection. So we solved this with a second addition to the Dotty compiler, a second type class that we call field typer, that basically maps label value pairs to a record type holding a single field. And this is like, if you have done type level programming in Scala, this notation shouldn't be any surprise. We have like an out type number here. So we demand to have like an instance of field typer, and then we can use the type member out here to use like the right hand side of the intersection type. So what happens when you call this? Well, the compiler synthesizes proof of extensibility. It synthesizes a field typer that does the mapping, and the result would be this intersection type that corresponds to the record type that we want. And with these two additions, we can provide a library allowing you to write code like this. You can create this record here. Instead of the extend method we have introduced on syntactic sugar, you can use this nice plus notation to extend stuff. You see it get a structural refinement type out of the box. And the really neat thing is that extensions works in polymorphic context. So here you have this polymorphic method add year that can add a year field to any R. It's just a abstract type variable R here, given that you provide a context bound saying that it will be safe to extend. So here, the compiler won't synthesize anything because you will already have an extensible in scope. And if you try to pass a record here that you really can't extend, you would notice it at the call site of this polymorphic method instead. So in this case, it's safe to extend, and you will get the correct type. If you have this record, it will not be safe to extend, and you will notice it when you try to call add here, because you can't create this context bound. So if I have time, yes I have, I will give you some benchmarking results. Since we're using, right, cool, thanks. Since we're using a hash map, Scala's immutable hash map as underlying data structure, what are the runtime implications of that, I mean, compared to classes? So we have created this benchmarking library that allows you to micro-benchmark a lot of different operations on records. We measure creation time, access time, update time, etc. But I will only show you a few results here. So first off, the time it takes to access a field against the size of the record. So in case of, for example, shapeless here, where the fields are stored as like a linked list, you clearly see that it has like linear access time in the size of the record. Worst case, of course, if you access like the last field. But maybe the most interesting thing here is that, well, here you have the nominal, a baseline, which is the nominally typed case classes, and the blue line here are our hash map-based records. So, of course, we cannot achieve the same performance as accessing a field on a nominally typed class, but it also, it's kind of the same as the cached reflection-based field access from Scala 2. So in this case, accessing values, we cannot achieve the same performance as nominal type case classes, but in some other cases, we're actually better than case classes. For example, with updating values. Since we want immutable updates, if you have a case class, you would have to copy everything if you want to update a value. But since we're using immutable hash maps underneath, we get effectively constant time record updates. You would have to have pretty large records to beat the case class performance. So the blue line here are our records, and the red line going up here is case classes. So above, like if you have really large records that you need to update a lot, you will actually benefit from using our records. Finally, we made, like, to give some perspective on the micro benchmarks, we made a macro benchmark, downloading 300,000 commit events from the GitHub API in JSON format, turning them to records, doing some data mangling on them, reading fields, updating, etc. And so in this like practical scenario, you see that so this is the time it basically takes to do this computation. And, well, of course, we cannot get down to the performance of nominal type case classes, but we're at least way faster than the Compostable Library, and the difference isn't that large. I'm a bit sad to see that we're also slower than shapeless, but it turns out that we spend like 95% of the time of this benchmark creating records, and that is extremely cheap to do in shapeless. So if we were to like update records or reading fields from huge records, this would look different, I think. So in summary, we have now a record constructor for record primitives. We have structural subtyping, type-safe extensibility, no dependency on the deprecated macro system, really small changes to the type system. I mean, we just add 2 compiler synthesized type classes, no changes to the syntax, and also this is a bonus one. You can subclass these records to provide your own backend. You don't have to use the default hash map. So you could have like a database underneath to like get the values from or store, or maybe a Spark data frame or something. And the stuff that I didn't have time to cover here, I mean, we have some syntactic sugar to make it nicer to use these things. We use like a broader display of Scala 3 features like type lambdas, erased terms, etc., more benchmarks. And we also have like a discussion of how our design goals actually affects the possible performance. if we have a different set of design goals, it might be possible to get better performance actually. Right, so check out the paper for more. Thanks.
Thanks for the speaker. We have time for a few questions. Bruno?
Hi. So I have two questions actually.
Yep.
So the first one is, have you seen, I've done some work that is closely related. Have you seen my work on disjoint intersection types and disjoint quantification?
I have not.
Okay.
Where can I find that work?
Well, disjoint intersection types is ICFP 2016 paper.
Mm-hmm.
Disjoint quantification is of 2017. We can talk afterwards.
Yeah, sure, that'd be great.
Okay. It basically provides a solution for your concat, the one that you
awesome.
gave up.
Yeah.
Okay.
Right.
So the second one is, what is the semantics of your extents when you have? So you told us about year of different types, int and string.
Yeah.
So you, but you haven't mentioned what happens if you already have a year and you append another year of the same type.
Right.
integer.
So in that case, you are allowed to do that, and we basically use the extend method to update stuff. So maybe I don't know if you can show that in this example, but it would definitely be allowed, since the only thing we require is that the new value have a subtype. So you can add a new value as long as it has the same type, basically. That is perfectly
And
fine.
what is going to be the type of that? It's going to be a record with one.
Right, so it will be the intersection of the old type and the new type. So you might end up with a value that has like well, no, actually you will get the more precise type, because if you have an intersection of like A and B, where B subtypes A, that would be like the same thing as the lowest type, right? So
it seems to me that you traded the white box macros for modifying the compiler, which doesn't seem like such a win to me. I think there's use cases for white box macros, and people are looking into actually having them in Scala 3. And for example, so one of the things that is being explored is match types. And I think using match types, it could be possible to add a type that have precisely that mirrors the semantics of the map, as in it's asymmetric and it extends things by overwriting types that are already present in the record. I just have a feeling that maybe we could do it like this. I don't know if you've thought about it.
right, I mean, so since we did this work with like the Dolly compiler, it's not clear what features we will end up having. And the only thing we know is that like the white box macros will disappear. But if there will be some macro system that would allow you to do this, and a macro system that like that we know is stable and also will work out great with like static code analysis tools, for example, of course it would be nice to lift this functionality out. But like at the current state, this is what we were able to do, right? Also, I think the most hacky one, if you're the hackiest of these two, is the field typer that actually just works as like a mapping from label value to record type. I mean, if you could provide some better way of doing that mapping with the Scala typer, I think that would be preferable. But this was like the practical, achievable thing.
So I'm afraid that we run out of time for other questions. We can take them offline.
Yeah.
Let's thank the speaker again.